To conclude our discussion of electron configurations of atoms, let's look at what happens to the configurations when we form ions, that is, we add or remove electrons from the atoms. We're going to break up the behaviors into two groups. The first are going to be the main group cations and anions, and the second will be transition metal cations. The main group ions are relatively straightforward. Atoms often gain or lose electrons to achieve noble gas-like configurations. A cation loses electrons and becomes positively charged. An anion gains electrons to become negatively charged. For example, lithium forms lithium cation by losing one electron. We remove the highest energy electron, which is the 2s1, and leave the two 1s electrons. This forms lithium plus. This lithium plus cation has the same electron configuration as helium, which is the closest noble gas on the periodic table. For another example, consider fluorine. Fluorine can gain an electron to become the fluoride anion. In this case, we're adding an electron to the system to form a neon-like configuration. So we have a 1s2, 2s2, 2p5 configuration to which we add an electron and end up with a 1s2, 2s2, 2p6 configuration matching neon for the fluoride anion. We say that atoms or ions with the same electronic configuration and same number of electrons are isoelectronic. For example, these four systems all have the same neon-like electron configuration, a 1s2, 2s2, 2p6 electronic configuration with 10 electrons. We can, for example, take oxygen, add 2 electrons to form O2-. We can take fluorine, add 1 electron to form F-. We can take sodium, remove an electron to form sodium cation. Or we can take magnesium, remove 2 electrons to form magnesium 2+. All of these are isoelectronic with neon. They have the same electron configuration as neon. Let's try a practice problem. What ion and electronic configuration does bromine form? So bromine has an argon core and then a 4s2, 3d10, 4p5 configuration. It's found right here on the periodic table. Go ahead and pause this video, attempt the question, and hit resume when ready. So the answer is that bromine likes to gain 1 electron to form the bromide anion, because that makes it isoelectronic with krypton. As we gain 1 electron, we're going to get the same configuration as krypton. Or put another way, we have 5 4p electrons in bromine. If we add 1 more, we're going to end up with a 4p6 configuration. Because we're adding an electron to form an anion, we are going to be negatively charged rather than positively charged. So that's why the answer is A. Let's try another example. What ion and electron configuration does magnesium form? Magnesium has a 1s2, 2s2, 2p6, 3s2 configuration. It's right here on the periodic table. Again, attempt this question and then hit resume on the video when ready. The answer is D. Magnesium would like to lose 2 electrons to form the magnesium 2+ cation because that makes it isoelectronic with neon. So as we take 2 electrons away out of the 3s orbitals, we're going to end up with a configuration that's equivalent to that of neon. So as you can see, this is answer D, where we've removed the 2 electrons to end up with a 1s2, 2s2, 2p6 configuration. As always, the behaviors of transition metals are a little more complicated. A given transition metal can often form multiple different cations with different charge states. A few trends do emerge, however. First, transition metals tend to ionize the valence s electrons before any electrons in the d orbitals. This is why +1 and +2 cations are common. For example, nickel can form a +2 cation. To do so, it ionizes its 2 4s electrons to form an argon core 3d8 configuration. Similarly, silver can form a +1 cation by losing its 1 5s electron. So recall, silver is one of those special cases. You might think it would have a 5s2 4d9 configuration, but instead it promotes one of the s electrons to the d shell to get the full d shell and ends up with a 5s1 4d10 configuration. So when it forms the ion, it loses the 1 5s electron in order to end up with a 4d10 configuration, retaining the full d shell. Now this behavior probably seems confusing since it appears to contradict the Aufbau rule. Right? We think of the 5s orbital as being lower in energy than the 4d when filling the orbitals. However, this really just highlights the complexity of quantum mechanics. These particular ions end up being more stable due to the subtle interplay among orbital stability and electron attraction to the nucleus versus the differences in electron-electron repulsion that occur between electrons in the same subshell versus different subshells. In other words, there's no simple explanation, but this is the reality. Some transition metals will also form cations with charges of +3 or higher. In those cases, they typically lose the s electrons and some d electrons. For example, iron can form either a +2 or a +3 cation. In the +2 case, it just loses both of its 4s electrons to end up with a 3d6 configuration. In the +3 case, it loses the 4s electrons, and then it also loses one of the d electrons to end up with a half-filled 3d5 shell. Let's try a practice problem. What are the electronic configurations of manganese and its 3+ cation? For reference, manganese is a group 7 element. Attempt the solution to this and hit resume on the video when you're ready to hear the answer. So manganese has 7 valence electrons. That means it has 2 in the 4s shell and 5 in the 3d. So it has a 4s2, 3d5 valence configuration around an argon core. To form manganese 3+, we're first going to remove 2 electrons from the s orbitals, and then we have to remove 1 more from the d orbitals. So we're left with an argon core and a 3d4 configuration. So in this case, the answer is D. To summarize, main group elements typically gain or lose electrons to become isoelectronic with the nearest noble gas. Anions gain electrons and cations lose them. For transition metals, it may be possible to form more than one type of cation with different charge states. The first 1 to 2 electrons ionized will typically be removed from the outermost s orbital, while any additional electrons come out of the d orbitals.